Here. Stoichiometry. This is a fun word to say. Sometimes we abbreviate it stoic. Okay. Stoichiometry is, if you're wondering, it's from the ancient Greek, from two words that mean element and measure. Okay. So literally, stoichiometry is about measuring elements. Okay. That's awesome. Stoichiometry is about quantitative studies, so we're going to be dealing a lot with numbers here. We're going to be doing a lot of math, just like on that cookie dough recipe that we were just working through. Okay, we won't be making cookies today. No. You need a properly balanced chemical reaction in order to do stoichiometry. Fortunately, you guys have already gotten through that chapter and did fairly well at that, right? Okay. Yes, you did. Okay. Mole ratios help to tell us the relationship of one substance to another. We're going to talk about it. But we can see a couple of things from this equation. There's a couple of meanings that we can take from it. We could take the meaning that's right down here, that 2 molecules of hydrogen plus 1 molecule of oxygen makes 2 molecules of water. Or since we can't really deal with molecules, we could deal with moles, right? 2 moles of hydrogen, so double Avogadro's number worth of molecules, plus 1 times Avogadro's number of oxygen gives me 2 times Avogadro's number of water. 2 moles to 1 mole to 2 mole. So we can talk about these ratios easiest by comparing moles. And you guys already know that moles are probably one of the chemist's best friends. All right, ready? So what that means is that when we do stoichiometry, we're going to be doing mole conversions. Mole conversions are going to be the most important thing in a stoichiometry problem. We're going to be converting moles of one substance into moles of another substance. I'm going to show you guys this. Okay, here are the examples that we want to work out. Should I give you guys a chance to copy that down before we start doing it? Okay, so here's how I would work it out anyhow. Pretty much the same thing as Brian said. We got 8 moles of nitrogen. Okay, so if you're working out a problem in Stoic, it's best to have a number, to have a unit, and the formula, because you're going to be switching from one chemical to another, so you want to keep track of that. Okay, we're going to definitely want moles of nitrogen on the bottom for the same reason as we do for any dimensional analysis. What's on the bottom cancels out what's on the top here. And we want to convert to moles of, in this case, ammonia, so NH3. All we have to do is figure out the molar ratio between ammonia and nitrogen gas. And it turns out that's already done for us up here, right? 2 moles of NH3. So I'm going to put that up here. And 1 mole of nitrogen gas. Those are the coefficients. Like Brian said, 8 times 2 gives us 16 moles of NH3. And it stopped right on NH3. There we go. Oh, okay. So with this one, we're going to do basically the same kind of math. 16.0, I'm sorry, not 16.0, 16.8 moles of nitrogen gas. What do we have to have on the bottom for units? Thanks for answering, guys. Moles of nitrogen, right? What do we want on top? Right, that's what it says here, moles of hydrogen. So moles of H2 goes on top. How many moles of hydrogen? 3. How many moles of nitrogen? 1, right? Because hydrogen says 3, nitrogen, there's a 1 coefficient out there. Okay, so 16.8 times 3 gives us 50.4 moles of hydrogen. And I should probably... Guys, with stoichiometry, if you need a flowchart, I gave you guys a flowchart handout to help with any stoichiometry problem possible. It's got 4 basic steps. Step 1, write the correct balanced chemical equation. Step 2, convert the given quantity to moles. That might not be necessary because the problem might already tell you it in moles. But it's possible they could tell you in grams. It's possible they could tell you how many particles, or they could tell you how many liters at STP. Okay. We already know how to deal with those three things, right? And convert to moles. The third step would be to use the coefficients to change from moles of one substance to moles of another substance. And then the fourth step is also optional. If you want to know the answer in moles, you can leave it in moles. But if they want it in any other quantity, you want to change it to that quantity. So you want to convert moles to grams, moles to particles, or moles to liters if the problem's at STP. Work out problem number 1 together real quick. All right. They're looking for, if I'm going to dissect the problem, and sometimes this helps, right? Grams of ammonia gas at the very end. So at the very end, I'm going to write grams of NH3. At the very beginning, they start us out with 3.04 grams of hydrogen. Again, that excess nitrogen gas is just telling me that I got plenty of that and I don't need to worry about it at all. So grams of, oops, tablet's not working nicely. So if grams of hydrogen goes on the bottom, the very first step says, if necessary, convert to moles. I'm not in moles, so I'm going to convert to moles of hydrogen. Molar mass of hydrogen is 2.02. 2.02 grams for 1 mole. That takes care of the grams of hydrogen and leaves me with moles of hydrogen. Basically, the second step after having the balanced equation is to convert from moles of one substance to moles of the target substance. Happens to be ammonia. We're going to use the coefficients. So moles of hydrogen should be 3. Moles of ammonia should be 2, based on the coefficients. Moles of hydrogen cancel. And finally, moles of NH3 can be converted to a different set of units. In this case, they want grams. So I know that the molar mass is 1 mole is 17.04, if I'm doing my math right. What's up? So ultimately speaking, the math that we have to do is 3.04 divided by 2.02, multiplied by 2, divided by 3, multiplied by 17.04. Wanting 3 sig figs because the first number was given with 3 sig figs, I'm rounding what the calculator gave me to be 17.1 grams of nitrogen. Grams of ammonia. The question asks, I seem to have lost my pointer. There it is. The question asks how many grams of nitrogen gas we're making. So we're going to toss that at the end of the problem, grams of N2, because N2 is the formula for nitrogen. They start off with 12.44 grams of hydrogen gas. So at the very beginning, we're going to put 12.44 grams of hydrogen. And again, this is important to write down the formula and to make sure that it's right. You can't just write down H, because otherwise you might think it's 1.01 for a molar mass. So in this first step, I'm going to try converting from grams to moles. So 1 mole of hydrogen says, ooh, I wrote that down wrong. I wrote 2.20. It should be 2.02 grams of hydrogen. Grams of hydrogen and grams of hydrogen cancel. We're left with those moles of hydrogen. Once I'm in moles of hydrogen, I can convert to moles of nitrogen gas. Okay. We're using the molar ratios from the balanced equation. So we're going to use 3 moles of hydrogen and 1 mole of nitrogen. Got to put those numbers in the right place. And moles of hydrogen and moles of hydrogen cancel. And then one last step. Moles of nitrogen can get converted to grams of nitrogen, because in this case they want grams. 1 mole isn't going to weigh 14.01 because nitrogen's diatomic, so it's going to weigh twice that, which is 28.02. And the moles of nitrogen and moles of nitrogen cancel. So the math in the calculator is 12.44 divided by 2.02 divided by 3 times 28.02. What did I write down? With 3 sig figs, I'm getting 57.5 as a rounded value. Ooh, shoot, I wrote 3 sig figs. How many should we have? 4.